I went around the world to understand the genetics of these athletes, and in that process uncovered the fact that there was also a lot of doping going on.
Hello and welcome back to the MGI podcast. It's Olympics season right now. The Paris Olympics have just finished and the Paralympics are about to start soon. So as everyone's talking about the history and the future of the Olympic Games, doping and drug use is a topic that we can't avoid. Joining us for this episode is Professor Yannis Pitsiladis from Hong Kong Baptist University, who's a member of the IOC's Medical and Scientific Commission. He's going to talk with us about his work on a transcriptomic approach to drug testing in sports. So hi Yannis, thanks for joining us. To start with, can you share a little bit with us about your background and how you became involved in the anti-doping research that you do?
Yes, so my name is Yannis Pitsiladis. I'm professor of sports science and sports medicine. I'm a professor at Hong Kong Baptist University in Hong Kong. And early on in my career, I was very much interested in questions why certain ethnic groups excel in sport. For example, in the 100 meters, it tends to be athletes, black athletes from Jamaica or the US that dominate that sport. And in the marathon, they tend to be from Ethiopia and Kenya. So I went around the world to understand the genetics of these athletes. And in that process, uncovered the fact that there was also a lot of doping going on. So I was working on genetics, doping, and I thought, well, could I use genetics as a means to make the testing more, let's say, more robust and actually be able to detect really the cheaters? And that's the way it all happened, So it was quite serendipitous by chance. And now we know that genomics technology is the most powerful technology in biomedical sciences. So let's use it. If it can be used to try and understand cancer, for example, let's use it as well to catch those who are cheating. That's really the background.
Excellent. So you're in Paris right now for the Olympics. So could you tell us a bit about what you're doing in Paris and tell us a bit about the Ollie House that you're in?
Yeah, so this is actually my sixth Olympics now. I'm a member of the International Olympic Committee's Medical and Scientific Commission, which its remit is to actually ensure the health of the clean athlete. So we know that elite sport can be bad for you at times or can even cause injuries, etc. So our role is to ensure that they are protected and they can compete with the knowledge that there is a system there to help them should they have any difficulties. And related to that, I'm a member also of the IOC's Games Group, which is the medical team at the Olympic Games. So the Medical Commission is obviously in the whole period of the 4-year cycle. But at the Games, there's this Games group, which we meet every morning at 8 o'clock to assess what happened the day before, to evaluate what is coming, and deal with all sorts of issues, from respiratory issues to COVID to, you would have heard a lot about the water quality in the Seine, the issue of the gender issues in boxing. All these topics that come up, we are the group that discuss these every morning and come up with solutions where we can.
Excellent. So a big part of your work has been about developing a transcriptomic test for doping. Could you explain what a transcriptomic test is, just sort of
Yes.
from the basics, and how it differs from more traditional doping tests?
Yes. So, I mean, in the last 2 decades, the World Anti-Doping Agency has really advanced the technology in terms of detecting substances that are in the body. And that works very, very well. They can detect, the equivalent of a droplet of blood in a Olympic-sized swimming pool. So very, very good. What they don't do so well is look at the impact of drugs that have large impact on the human body and therefore performance, but leave the body very quickly, so typically in 24 hours. And so I came up with this idea of looking at genes as they switched on and switched off based on these drugs that I say leave the body very quickly. They leave a molecular signature And that is called the molecular signature in terms of switching on and switching off of genes is called transcriptomics, or it's the gene expression, should I say. To make it very, very simple, it's like a dimmer switch in a hotel room, making a light brighter or a light less bright. Genes get overexpressed or they get downregulated. And they typically do that depending on the drug that's being used. And that signature is what we're able to detect even weeks after the drug has left the system. And that's the basis of the test, because currently for blood doping or looking at erythropoietin or EPO, which is the drug of choice for endurance sport, those who wish to cheat. I said the drug is gone within 24 hours or 48 hours, but the impact is there for maybe 120 days, the lifetime of a red blood cell. So using transcriptomics, and now we've published a number of papers showing this, we can see that molecular signature weeks after the last injection of the drug that we've actually done in the laboratory. And now what we're doing is just confirming that indirect test isn't going to wrongly accuse an athlete of cheating because, for example, they've gone to altitude. So now what we're doing is we've taken athletes to altitude. We're looking at their transcriptomic response or their molecular signature and making sure that the molecular signature of doping is different to the molecular signature of going to altitude or different from training, so we don't wrongly accuse an athlete. And the technology that we are currently using is supported by MGI here in Oli House in Paris. We have some of the technology that we plan to use for the transcriptomic testing, including our robotic system, because the other advantage of the technology we are currently using is that you can, from blood sample right through to the report, you don't actually need a human to do anything. So it also helps us get away from human error, which sometimes may happen. So we have a very sophisticated robotic platform from blood sample to report that we've published now in a number of papers that it works. And we're very excited the future. We just need to completely validate and replicate the process, which is what we're currently doing together in partnership with MGI. And we're very excited about the future because of that.
Amazing. So what are some of the practical considerations when you come to integrate this kind of testing with more traditional tests for doping? If they come into conflict, does that raise any sort of issues or challenges, or what's the potential of sort of combining it with more traditional strategies for testing?
That's a really excellent question. Currently, the process that I just referred to in terms of blood collection is called the athlete biological passport. So like a passport that you'd use when you're traveling, it's the same thing athletes have to do. So every single day, even here at the Olympics, they have to declare where they are. Typically we know where they are because they're going to be in the Olympic Village, and the testers will come and collect a sample from them. And that typically is done over a period of time. And when you have 6 samples, for example, you can see the normal fluctuation in these hematological profiles. Typically, the ones they measure are hemoglobin and reticulocytes, which are premature red blood cells. And that's what's currently being used. The problem is that these are very easy to measure parameters. You can do it at home. You can do it in the side of a football pitch. And those athletes who want to cheat are doing it, looking at their blood, assessing exactly the way that let's say the World Anti-Doping Agency is going to do it. And then they'll make sure that they're available when they know they're not going to be found guilty of cheating. So they are testing themselves and ensuring that they will be clean and going out and be tested and knowing they're not going to be caught. What we are going to do here is take the same blood sample, but instead of only using those parameters, so we're also going to use those parameters, so we still use the traditional test. We're going to look at the whole transcriptome. That's the beauty of genetic sequencing. We can look at every single gene that's switched on and switched off. And you can't do this at home. You can't do it in your garage. So I often say to those who are a little bit skeptical, who say, Yannis, the genetic test is not going to work. I say, in the worst case scenario, I know it's going to work, but let's say it didn't. The fact that we can do something that they can't do means that they're not going to sleep well at night. So that it means that they are not going to be cheating because of even the doubt they will have that this technology, which they can't replicate in their homes, can potentially be used to catch them over the next years. And be reminded that here in the Olympic Games, those blood samples are stored for 10 years. 10 years. So, I mean, I know now with the support I'm getting from MGI, I believe we're going to be able to do this well within the next 4-year cycle to the LA Summer Olympics. I'm even comfortable and confident that we could do it in the next cycle leading up to the Milano Cortina Winter Olympic Games, because that's also an issue for us, the Winter Games. So I'm confident we can do it in a shorter period of time. But the samples here in Paris will be stored for 10 years. So even if I don't do it as efficiently as I know we can do it, I have 10 years to develop the test. We won't need 10 years, So yeah, that's how we're going to integrate. So it's really, really exciting. The other aspect, also quite interesting as well to comment, is that a transcriptomic test that I'm referring to in preparation of the blood sample doesn't need refrigeration. So once the sample is collected and you deactivate, or you basically, you basically are controlling for the breakdown of RNA, the sample doesn't require expensive refrigeration in terms of transportation and all the rest. So it's actually an easier process. Also, the World Anti-Doping Agency in the last few years have invested in what is called a dried blood spot approach. So instead of collecting a big blood sample, they're just collecting a small droplet of blood. And we want to integrate with that testing as well. So take a dried blood spot, extract RNA, and do our transcriptomic test once we know what genes we're looking for. So there's many ways to integrate. So what we don't want to do is reinvent the wheel here. What we're trying to do is use the best technology available that's been made available to us thanks to the partnership with MGI, and perfect and evolve the current testing, which needs modernization. And that's what we plan to do.
Yeah, it's fascinating. So speaking of the sort of time frames, you say these samples are stored for long periods of time after the competitions in many cases. A lot of the sort of public high profile cases of doping have come out several years after the actual competition. Do you think this genetic testing approach could maybe shorten that timescale of like when these can be found, and like maybe even within a competition, so that if people are winning medals that they shouldn't technically have won, obviously whoever came in 4th place, 5th place is missing out. Do you think there's scope for shortening that time frame so that these things can be caught quicker?
Another brilliant question, and I want to remind you and our audience what happened during COVID. You remember initially the testing was a long process. We had to wait for days to hear the outcome. I would say we're at that stage now where we at the days scenario. So basically this technology will take us, let's say, potentially a day and a half to get the result. But I'm very confident that, again, in the time frame I just referred to, that we can do the test in hours, which actually means my ideal scenario is that the athlete competes, and before they put the medal around their neck, that we know the test, and this time the test works. We don't have that situation where 4 years later, there are actually athletes at these games that are getting the medal for the last Olympics. Now imagine how they feel. Their moment is lost. And if you speak to the athletes, you say, how do you feel? They don't feel good. Their moment is gone. It's too late now. We want to avoid that scenario. And that's really the beauty of this technology, that, I strongly believe in the next few years, we can do the test on the side of the pool, almost, on the side of the track. Wherever it is, a test that cannot be manipulated, that does work, can be done quickly and robustly. And incidentally, because you use the word genomics, or genes, we are looking at a transcriptomic test, so looking at gene expression. the beauty of this approach as well can also make us look at where the sample is from that athlete. And that's also the beauty of our technology, because at the end of the day, what we know, there have been very many cases where athletes have tried to, they attach, artificial penises to themselves. So when they're actually urinating or providing a blood sample, they try and actually, manipulate the sample. What we can also do using a genetic test that can be integrated in our testing is ensure the sample has come from that person, and there hasn't been any kind of switching of samples, which has also been done over the last few years. So, this is the beauty of the technology: quicker, better, and also, I should mention, cheaper. A typical, whole blood test currently can cost, anywhere between, $150 and $250 to do. I think in time, we'll be able to do a whole transcriptomic test, in $10. With $10, that's coming. It's not there yet. It's on its way. So when I hear as well that omics technology, these kind of technologies that we're talking about today, are not practical because they're too expensive, that is historical. I remember the beginning of my genomics career, it cost, $1 million or even $100 million to sequence the genome. Now, we can do that for a few $100. And I know that, by the next Olympics, it'll probably be under 50 and maybe even $10. So cost is not going to be the issue either.
So when you're choosing the sequencing technologies, the sequencing tools that you're using for these tests, is the main factor that you're looking for, that the sort of speed and the cost per test, is that the main factor? Are there any other things that are important for you to consider, when you're sort of, as you say, you're working in partnership with MGI, like when you're selecting the tools, like what are the important things that you're looking for there?
Yeah, another great question. Going back historically, when we started this work back in 2008, 2012, that period of time, those 4 years, we didn't have access to sequencing at the time, so we started off using arrays. And you know what? The arrays work well, so if we had to only use arrays, we wouldn't get the same amount of transcripts, but basically, the test would still work. While all the approaches worked, so we had, really good discernibility using the arrays, using MGI sequencing. MGI sequencing was just better. It allowed us to get more transcripts that differentiated doping from altitude as well as from the baseline, because each individual also acts as their own control. So, so based on that, I chose MGI technology, and also they've been very responsive to our call for partnership. They are helping us create a platform that is going to speed up the whole process, and even helping us develop a fully automated anti-doping platform. And that is also the reason why at Hong Kong BU we've invested 52 million Hong Kong dollars to create the new state-of-the-art MGI lab, almost dedicated to anti-doping. So we're investing ourselves real money in doing this, plus the support we're getting from MGI. And so we're very excited.
Excellent. So we've spoken a lot about, obviously, the speed and also in general sort of the availability of this technology, how that's impacting its use in this field. Have you also found that that's impacted the development process? So when you're looking into improving the tests, developing new sorts of tests, obviously that faster turnaround, does that also help in that sense? And when we're talking about things like hybrid testing using genomic information as well as transcriptomics, things like that, any sort of new approaches that you're working on, does that availability help there as well?
Yes. No, again, a super question. I mean, due to the constraints that we've had, typically financial, typically access to this kind of technology in the past, now no longer the case. We started off with what I call low-hanging fruit. So looking at the transcriptomics alone as one of the omics technologies. But what we're hoping to do, thanks to this partnership, is integrate the different omics. So look at genomics, transcriptomics, metabolomics, proteomics, epigenetics, integrate these different omics, use very sophisticated bioinformatics informed by machine learning and AI, and actually learn from our clinical trials where we're actually giving EPO. So we are doing the doping internally in the lab, learn from our big data sets that we are generating and speed up that whole process. We've also collected over the years, we've been doing this now for almost 20 years now. We have one of the best biobanks in the world, now located in Hong Kong, where we can go back to the freezer, get some samples and test them again and again and again. And that biobank is ever increasing. So looking at multiple omics, newer technologies, plus adding the biobank and doing new clinical trials, which is also what we're doing, we're very, very excited that we're going to be able to, again, fast track that process. And I should also mention some of our newer work in terms of the clinical work, where we're looking at this notion of coming up with a test that can, or not even a test, but also understand a phenomenon called muscle memory, which is when in an animal model, if you inject a mouse with testosterone, and they obviously benefit from that, then you remove testosterone for, let's say, for 1/3 of the mouse's lifespan, and then you basically test them after that period of time, you find that the previous drug trial they had a very long time ago still has benefits. We are currently trying to confirm that in humans. If we do that, our testing process and catching those cheaters, we could also potentially have life bans. And imagine that deterrent. So longer storage, better technology, cheaper technology, quicker technology that can't be cheated, and then longer bans. I mean, you can see where we're going with all this. I mean, this is making anti-doping as fit for purpose as possible. Those are the developments that are happening, and I'm very, very excited. And actually here in Paris, actually in this room that I'm sitting at the moment here at Ollie House, we also met with the World Anti-Doping Agency, the head of science and medicine, Olivier Raban, also our friends at the ITA, which is the International Testing Authority. I discussed these developments that I'm sharing with you today, and they are equally excited about this, and we said, let's work together. Because that's the other thing I should mention. What we learned during COVID was that, by different organizations working together, even competitors and industry, by working together, we solved the COVID issue. Be reminded 100 years ago, during the Spanish flu, which is the previous major pandemic, maybe 50 to 100 million people died. This time, about 7 to 8 million died. That's too many people anyway. But that's a big difference in numbers compared to 100 million. Why? Because of concerted approach, R&D, working together, the best industry. Well, you know what? For the first time, we are doing that. At Hong Kong BU, together with our partners, with International Olympic Committee, with RTA, with WADA, with industry, we are all working together. And that's been the change. And we have the money now. Before, we were only waiting for money from the World Anti-Doping Agency. I mean, their budget since their conception some 20 years ago for research is somewhere in about $90 million US. I mean, that's peanuts compared to what you need. Now we have real money. And so putting all this together and the right resolve, and by the way, we need to get it right now, because if we don't get it right, there's a big threat coming. What is that threat? Some of your audience would have heard of the enhanced games. In 2025, there'll be these anti-Olympic games, is what I call them, where they're going to allow drugs, any drug you want, the athletes can use. And you know what? If we don't clean up the Olympics and elite sport, then actually athletes will say, well, I'll go and compete in the enhanced games, get paid a lot more money, because in the Olympic Games, athletes don't get paid to participate, et cetera, et cetera. So we have to get this right. And I believe for the first time in my career, spanning 25 odd years, I really feel confident that we have all the pieces we need now, thanks also to MGI, that we can do the job now.
Excellent. Yeah, it's a great outlook. So you were talking before about how this improved testing essentially becomes a deterrent as well. So as well as catching people who have cheated, you're preventing people who might think of cheating. You're sort of decreasing the number of people that might even consider it.
Yes.
Because they're aware that the testing is that much better and that much harder to get around. Is it important then as well to have an educational or sort of outreach aspect to this as well for athletes, so that they get to know how the new kinds of testing, how modern testing works, and how difficult it is to cheat?
Another brilliant question. And education is so important. Education, education, education. However, education without proper testing fails. Because, if you're educating about, why athletes shouldn't dope, the testing process, if the athletes know that, those who are cheating are not being caught, that education becomes meaningless. So what we need is, I would argue we need, think of a three-legged stool. We need three main pillars. One is education. Exactly your question. The second, we need anti-doping testing that works. It has to work. But even those two, if you have a three-legged stool that's only got two legs, you fall. You need the third one. What's the third one? We need proper science and medicine to keep athletes safe and to have the best technology to allow them to break records within the rules. Athletes want to run faster, jump higher, etc., etc. So you need those three pillars. So education, enhanced testing, better testing, and you need science that helps with peak performance. Add those three together, then you really get the message across. Any of those three missing, you fail. And since we are talking about education, the same applies in terms of educating the public as well about the real advantages of genetic testing and the whole genetic or omics technologies. The public are quite terrified and ill-informed about genomic technologies. They fear that, this technology is going to harm them, etc., etc. And I think we need to indicate there's actually not much difference between any kind of clinical test they do when they go to a hospital and an omics-based test. It's the same kind of principle, at the end of the day. And so education is what we needed and what is needed to also indicate that, we need the very best technology like genetic sequencing to really understand disease, to prevent doping, and the public need to be part of that journey. So we need education, absolutely. And one of the reasons also we had an event here in this room on innovations that are integrating or coming into the Olympic Games is to really make the public be aware of that these technologies are essential. But like any new development, there's always the second side. There's a lot of worry about AI, the dangers of AI. Well, AI also has so many positives that can actually make our lives so much better, quality of our lives, and help us cure disease and catch the dopers. The same with other technologies like, nuclear energy. Nuclear energy is amazing for fueling our homes during the winters, but also you can create nuclear weapons. So, we need to harness the technology, understand it. And us professors at universities and organizations like the International Olympic Committee and the World Anti-Doping Agency, we need to understand the technology before the cheaters do. And so it's very, very important that we understand the technology, we own the technology, and we educate on proper use of this technology. Remember, as university professors, we can't just collect a sample from anyone. We have to go through typical ethical approvals. These tend to take months. We treat the samples properly, we store them properly, and we also eventually, destroy the samples according to proper procedure. So, we want the athletes to engage with us, and that's why we're also here doing educational programs. So I would say probably 30 to 40% of my time here in Paris is on education. So I'm delighted that we're actually even doing this interview, and I hope that I can, help, in one sense, convey those messages.
Yeah, absolutely. So finally, then, just to sort of wrap up, what are you going to be working on next? After these games, like, what are the sort of focus points for your research going forward, and where do you think the most promising areas for development might be? Looking forward to the next Summer Games, or even the one after that. Over the next sort of decade or so, where do you think this could go for the future of sports in general?
Yeah. So actually, also at the games, and we haven't had time to talk about that today, but we're also measuring what I call the phenome. The phenome is actually, the response of the athlete or the individual. So, for example, here at the games, we are measuring very carefully. We're using very sensitive technology. We're measuring the microclimate of where the athlete's competing. So we've actually placed, for example, weather stations all over the venues, even on the official boat that was actually following the athletes in sailing. We've instrumented some athletes who have volunteered to be instrumented. They've actually ingested a sensor that measures body temperature. They're wearing skin sensors for skin temperature. We're measuring heart rate and various other things. And all of those together are called the phenome. So in addition to the phenome and the genome and the transcriptome, if you integrate these two things, or these two different parameters, with AI, you can start differentiating the response of a group of individuals. And that's really what is exciting. I call it individual response or responder response, and it's really trying to understand why in a group of athletes, one person maybe gets sick, another one doesn't. And we saw that in the CN. The last few days, some athletes appear to get GI problems by swimming in the river here in Paris. Others didn't. Why is that? What is that individual response? So I think what's coming, and it's already here in some ways here in Paris, thanks also to our group, is integrating the very best technologies, the genomics, the other omics, the phenome with AI, and making predictions rapidly and in real time. So I want to be able to say in real time, while the athlete's competing, who is going to fall ill, and there's a team there ready to catch them before they fall down. And even maybe by the next Olympics, but maybe it'll take a little bit longer, being able to stop someone before they end the competition to protect them from being seriously hurt. We're not there yet, but, already in some sports, like in boxing, sometimes the officials intervene, or the coach will throw in the towel, for example. Well, let's use technology to actually help the athletes. Because you know what? Athletes will do almost anything for that gold medal. We need to protect them from themselves. Because you know what? Now they may say, I'll do anything. But, in 20 years or 30 years down the line, when they're suffering, when they can't actually get the spoon of food into their mouths, they may say, was it really worth being hit that hard on the head repeatedly? Now they're not thinking that. So we need to protect them. We have a responsibility to protect them using the very best technology. And I'm very proud of the work we're doing as the International Olympic Committee's Medical Commission and the Games Group in doing that. But we need to have better tools. And we're here in the Olympics at the pinnacle of the sport with our partners developing the very best technologies so we can protect every single athlete. And by the way, the spectators and the officials, the workforce. Actually, around about 30 to 40% of those who are falling ill at the games are not the athletes. They're the workforce, those who are actually standing at the gates all day long in the sunshine, very difficult conditions, making the games function. The officials who are sitting all day in very difficult conditions. So let's perfect these technologies. Let's make the technology part of the clothing of the officials, or let's modernize. And my final remark would be, these technologies will be the same technologies we want to adopt in our homes. I can see in the next decade, all of us owning a genetic sequencer in our homes, that'll be actually looking at our transcriptomic response, our phenotypic response, and telling us, and informing us what we can do to keep our families and ourselves safe in the more difficult conditions that we'll be living around the world. Global warming is upon us. We need to protect ourselves. We need to find ways to deal with pandemics. Well, sport is an excellent model where we have to keep all these athletes who are coming from every corner of the world safe under very difficult conditions and security at the same time. So if we can get our technology to work in the Olympic Games, they can work anywhere. And that's why I've been fighting sometimes, to get the federations to modernize, to allow us to integrate the technology at the Olympic Games. Some federations will say, okay, Yannis, this is great, but you can do it not at the Olympic Games. Do it at a smaller event. I say no. We should also do it at the smaller events. We should do it in the laboratory, but we need to do it at the very best and the most difficult events to really push the technology, because the technology also is not fit for purpose. We need to redesign the technology. A lot of the technology we have here today in Paris, I guarantee you will not be the technology we'll be using in 6 months from now. If I didn't bring it here to the games, I'd still be using the wrong technology in 6 months' time. We need to pioneer. And some of those same companies are here with us. MGI is just one of them. A lot of the other companies are here piloting the technology. So we are very, very excited about what is coming. And as I say, sport is one of the best opportunities for us to really perfect that technology.
Amazing. So thank you so much, Yannis. That was a really fascinating discussion. Thanks for your time and hope you enjoy the rest of the games.
Thank you very much. And it's been a real pleasure. Thank you.